So now what we want to be able to do is predict the pH of weak acid solutions. So let's just do it with an example. What is the pH of a 0.50 molar aqueous solution of acetic acid, that's CH3COOH, and the Ka of acetic acid is 1.76 times 10 to the negative fifth. Let's see how it goes.
All right, so we want to know what is the pH of a 0.5 molar aqueous solution of acetic acid, where Ka of acetic acid is 1.76 times 10 to the negative fifth. So whenever we want pH, we know that really what we're after is the concentration of hydroniums, right? pH is the negative log of the concentration of hydroniums. So if we could get the concentration of hydroniums, we can plug that value in and calculate our pH. And so the question will be, well, where do the hydroniums come from? They're going to come from this acetic acid reacting with water. We know hydroniums always come from acid reacting with water. So I can write out my reaction, CH3COOH aqueous plus water. And we know that that's going to make it's going to react, this hydrogen, this acid, acetic acid, is going to lose its hydrogen. So it's going to become CH3COO minus, the conjugate base of the acid. And I'm also going to make hydroniums. And so we want to know what the concentration of hydroniums is. So we want to know the amount of product that will be produced. So the question is, how much product do I make based on the reactants? And there's two ways to do that, either a stoichiometry type problem or an equilibrium type problem where you're having to use an ice table. And we can tell what we need to use based on the type of acid. The Ka in this case, we're told, is less than 1. That means acetic acid is weak. It's also not on our list of the 6 strong acids, but it is an acid, which means it has to be a weak acid. So we can tell that there's a couple ways we can tell acetic acid is weak. If we're given the Ka, since that's less than 1, that tells us it's going to be a reactant-favored equilibrium, and we're probably not going to make that much hydronium, and so we'd have to use an ice table to figure out how much hydronium will be prepared. So whenever you're dealing with a weak acid solution and you want to determine the pH of it, you always need to use an ice table because it is a reactant-favored product and we're dealing with an equilibrium type situation. So it's going to be ICE. So our initial concentration of acetic acid is 0.50. That's kind of how it was cooked up or how we made the solution. Water is a liquid, so it doesn't matter. It doesn't show up in our equilibrium constant expression. We start, basically we're imagining we start with only acetic acid, so we get zeros on the product side. When we're determining the change, the direction of change, because there's zeros over here, plus and plus with a minus over there, because the shift has to be to the product side because I start with no products. There's no acetate initially in the solution. Plus x, everything has a coefficient of 1. That's kind of always generally the case for acid-base chemistry. If you remember, we only transfer 1 hydrogen or 1 H plus at a time. And so we end up with this expression. 0.5 minus x for my acetic acid, plus x for the acetate, and x for the hydroniums. So the whole point of the ice table is just to get those algebraic expressions, those x's, that we can then plug into my Ka. So the Ka expression comes from the reaction. So the conjugate base is a product. Hydronium is my other product. And I divide those by the concentration of acetic acid at equilibrium. So I'm going to take these values, plug them in. My Ka is going to be equal to x times 0.50 minus x. I can multiply those x's together, and I end up with Ka is equal to x squared, 0.50 minus x. And so this is, if we kind of take a step back and think about what we've done so far, we have an acid reacting with water to make the conjugate base and hydroniums. And we're saying it's a weak acid, so it's an equilibrium type description. We have our ice table, get the algebraic representation, plug those into the equilibrium constant. Remember, these Kas always have the same form for every single acid. It's conjugate base concentration, hydronium concentration, divided by the initial acid. So the ice table, when we set it up, is always going to look like this general setup. The initial concentration, you're always going to shift to products, and there's always going to be just the single x's. So this x squared over the initial concentration minus x is generally how the ice table will evolve, or what the output of the ice table will look like for a weak acid problem when we're trying to determine the pH. One of the other things we can think about is looking at this is the K is always going to be small because it's a weak acid. That's the whole point of this thing being a weak acid. So for weak acid problems, you're always going to want to make the approximation, because the whole point of a weak acid is that you don't make a lot of hydroniums. So you're left with primarily the initial acid, right? Most of the acid that's in the solution looks like an acid. It hasn't yet donated the H+. So you can make the approximation that 0.5 minus x is going to be approximately equal to 0.5. If you don't make this approximation, you would have to use the quadratic formula to solve this problem. That's a lot of work. It's a lot of steps, which increases the chance of making a mistake. You get the two answers. You have to figure out which one you want to use. It's a long process. You'll always want to use this approach because it means we don't have to use the quadratic formula. It makes the solution many fewer steps. So since it's fewer steps, it's easier or a less chance to make a mistake. So plug that in. We get Ka is equal to x squared divided by 0.50. There's only a single x. There's only a single variable left. So that's going to be easier for us to figure out. So what we're going to do is we can take this. We have Ka is equal to x squared divided by 0.50. I want to isolate out the x. So Ka times 0.50 is equal to x squared. So I get that the square root of Ka times 0.50 is equal to x. And Ka, normally you can look at, if we were told it was acetic acid, remember the Ka, the value for that dissociation constant, it just corresponds to the identity of the acid. We're also given it in the problem, 1.76 times 10 to the negative fifth. So we can plug that in. X is the square root of 1.76 times 10 to the negative fifth times 0.5. We get, if we do the arithmetic on there, if we plug it all in, 3.0 times 10 to the negative third. Which is great. We've got an answer for x. One of the things that we want to do is we want to check to make sure our approximation is valid. And it's the change divided by the initial. So the change was the x that we had, 3.0 times 10 to the negative third, divided by 0.5 times 100. I'm just trying to figure out the percentage here, what that percent representation is. And I get 0.59%, which is less than 5, which means my approximation checks out. So I do need to be, for my approximation to be valid, it needs to be less than 5%. When you're dealing with weak acid problems, you can almost always get away with doing an approximation unless your weak acid concentration is really low, or that initial concentration is really low, or it's on the stronger end of the weak acids. You know, we have our table of acid dissociation constants, so something higher up on that. So we have our table. So like if you're doing like HiO3, where like that Ka is not that low, it's less than 1, but not that small. You may have issues there with getting away with using it, but something like acetic acid, which is even 10 to the negative fifth, isn't even that low. You can still almost always get away with doing the approximation. And still, even if you can't, it's worth it to try, because if you're going to do the quadratic equation, that's a lot of work. might as well see if you can get away with an approximation before you do all that work. So that checks out. So the X is valid. We can use it. So what we can do is we can use that and go back. Previously with ice tables, we've been able to say, okay, well, the concentration of acetate is equal to X. And so that's going to be 3.0 times 10 to the negative third molar. The concentration of hydronium is equal to X. So that's going to be 3.0 times 10 to the negative third molar. And the concentration of acetic acid, that's still in solution, is 0.5 minus 3.0 times 10 to the negative third, which it just ends up being 0.50 molar. Again, the approximation was that this didn't really change it, and that holds true. And so we end up with these values. But the thing is, we didn't want all these values previously when we were dealing with like ice table equilibrium problems. We wanted all the concentrations. But in this case, because it's applied, I'm dealing with an acid, what I really want is the pH. And so really all I need is this value right here, that hydronium concentration, because we can take that, and what we can do is we can plug it into the fact that pH is the negative log of that concentration of hydroniums. So we get negative log of 3.0 times 10 to the negative third, or I get that the pH is equal to 2.53. And so we've seen previously that what ice tables allow us to do is to determine what the concentrations will be at equilibrium. In this case, that at equilibrium is what the properties of the solution are, namely what the pH is. And so this is a pH gives us a description of what the equilibrium looks like, how many hydronium ions I have, what their concentration is, how that's different from neutral in our pure water sample. And so that's generally what we're kind of looking at or what we're dealing with here. And so in this case, the ice table gives us the concentration of something at equilibrium, which informs a property. And whenever you are trying to determine the pH of a weak acid solution, you will always need to use an ice table to go through this process. And it's almost always going to follow basically this exact same process because the reaction is always the same. It's the acid reacting with water to make the get base and hydronium. The equilibrium constant always has the same format because it's the same reaction. You can almost always make the approximation. You always should try to make the approximation. You want to, so this algebra is almost always going to follow the same pattern. You take the square root of the dissociation constant times the initial concentration of acid to get the X, check your approximation, and then you really don't have to do all of this. Really, all you want is the hydronium concentration because that's the only thing that goes into the pH. Now, if you were asked, what is the acetate concentration? What's the acetic acid concentration? You would, want to write those out. But if all you want is the pH, you only need the hydronium concentration, plug that into the equation, and you get.
So when we're dealing with weak acids and we want to determine the pH of the solution, it is going to require an ice table. It is an equilibrium problem, but the reaction of a weak acid with water is always going to be the same. So an ice table is always going to be set up the same way, and the algebra problem that we need to solve will always look the same, right? We're always going to have this x squared divided by the initial concentration minus x. And solving for x was what actually allows us to get the pH because that's the concentration of hydronium. In terms of solving the actual equilibrium, the algebra problem to solve for x, sometimes you may have to use a quadratic equation, but we can almost always use the approximation method because it is a weak acid, which means Ka is likely small. That's the whole point of dealing with a weak acid. There are fringe cases, really low concentrations of weak acids. You can't use an approximation, or kind of the stronger weak acids. But for the most part, you can almost always get away with using the approximation, which makes solving the algebra that's on the back end of the ice table more straightforward than some of the kind of more nasty equilibrium problems we had seen previously, generic in chapter 13. So the ice table always looks the same, and when we're kind of thinking about solving ice tables and dealing with weak acid problems, we've always been kind of looking at like what are the concentrations at equilibrium, or say what is the pH in the case of a weak acid problem. But when we're really looking at this equation, there is actually more than one variable here, right? X is what we're usually solving for. That is our concentration at equilibrium. In this case, that would be, you know, something related to the acidity of the solution. But the thing is, when we're dealing with an acid-base problem, we can measure some aspect of equilibrium. We can measure the pH, which can tell us what the concentration of hydronium is at equilibrium. So while we can use ice tables and the methods we've seen here to come up with what is the pH of some solution going to be, if we have a given solution, we can measure the pH, and then we can figure out what equilibrium looks like. Then we can see what the other two variables in this expression are. First is the Ka, which is dependent on the acid used, right? We've always known what the acid is previously, or base or whatever it is, and that gives us, well, here's what the Ka is. We can look it up in a table. And then the final thing is the actual initial concentration of the acid, how you tried to make this solution, what kind of the recipe is. And so we can kind of think of these as three kind of ideas. What acid are you using? You know, what is the chemistry you're dealing with? What is the initial concentration? And then what does equilibrium look like? And those three ideas are all related together. What we looked at here was taking, I know the acid, I know the initial concentration. What does equilibrium look like? What's the pH? It's a similar prospect for bases, where X is just the concentration of hydroxide, which you could measure the pH or relate pOH and relate that to the pOH. So in this example that we just looked at, we knew the acid, we knew the initial concentration, right? How much acid we started with. We were able to use those, plug those in to figure out what equilibrium will look like if we make this solution. That, namely, calculating the pH. What are the properties of this solution? We could also know how much acid we start with. We can determine what equilibrium looks like, namely by measuring the pH experimentally. We can use that to figure out what the acid is. Ka is a property of an acid, and so if we can calculate the number that this acid has a Ka equal to something, we can look that up in a table and figure out what the acid is. So you can figure out the type of acid, the name of an acid, by knowing about the properties of the solution that it creates. Finally, if we know the acid, and we know what equilibrium looks like, right? What the pH is going to be at equilibrium, then we can determine how much acid we need to use to obtain that pH. This is something along the lines of kind of what is the recipe? You know, you're going to use a certain acid and you want to have a certain pH. Well, what sort of concentration of acid do you need to start with? Okay, again, no participation questions in this video, but we got one video left. Maybe a participation question in the last one. Maybe we'll go out with a little tag on the end. See you in the last video.